Okay, so after the recent video which I posted about my major project ElementJS, a lot of people did ask me how did I get started with it or how they can get started with it. So this video in the same light to help you give you an idea how you can get started with creating your own engine, physics engine or your own physics library if you want to. I honestly don't recommend it, but if you want to, you can, right? So this will give you an idea, and what we're going to do today is we're going to create a simple ball or a simple point, and we're going to add very basic physics, which is gravity, friction, and some bounce to it. And we're also going to do edge detection so that the ball doesn't run off from the screen. And we'll also have a look at the underlying concepts behind it. So before we get started, I have created a folder called Verlet, and in that folder I have two files, and these two files are one is the index.html file, and the other is your JavaScript file, Verlet.js, right? And both are pretty simple. This code isn't anything complex. In the HTML file, I have the basic boilerplate code with just a canvas tag in my body, and which is encapsulated in a class, in a div class, canvas host. I also have some very basic styling to my HTML and body with margin 0, padding 0, and overflow hidden. If you don't want to do this margin 0, padding 0, make sure that you at least do this. You give overflow hidden to your page or to your entire HTML document. And next step is you might want to give display block to your canvas. It's going to make it at least a tad bit more responsive on mobile devices. Next thing that we need to do is we need to create your JavaScript file, which is actually the heart of the project. Now, first thing that we are doing is we're creating a window on load function, and inside it we're creating four variables. These four variables are pretty straightforward. Two of them are width and height, which are essentially equivalent to your device's height and width, right? Basically, you have resolution, and your device's resolution is also getting equated to canvas's width and height. The canvas is basically going to be equivalent to your device's width and height, and it is also going to be equivalent to width and height, these two variables that we have created here. We also have a variable called canvas, and it's actually equivalent to the canvas variable or canvas tag that we have declared and defined in our HTML file. We won't be needing our HTML file anymore, so we can just like put it aside. We'll be just focusing on our JavaScript file here. And we also have this context variable, which is just equivalent to 2D data. Context of our file is two-dimensional. Next, the important thing that we have in our JavaScript file and our window on load function is the update function, which recursively calls itself from the request animation frame function. It is an inbuilt function of JavaScript, which is used with Canvas, right? We also have this another line, context.clearRect, and where we are supplying 0 coordinates and width and height. This function is used to essentially clear the canvas. So if there is anything which was already drawn on the canvas, this line is used to clear it up. Except we're calling the function here, right? From this line, from line number 9, we're calling the update function. Then it is always stuck in a recursive loop unless you close the page. Anyway, so what our objective for today is, let's just say that we have a ball, right? This is a ball, and you throw it upwards, and then it obviously comes down because gravity, right? Now we can calculate the exact position of this object at any given time t, using the equation minus 16 t square plus vt plus k. Okay, so this is the equation that we have at any given time t, but the catch here is that should know the initial position of the object and the final position of the object. In such a case, we can use this equation to essentially figure out that where the object is at any given time t, like I said. But what if there is an object here and there is an object maybe here, right? So when we throw our ball up in the air, the ball might collide with this object, and then either it can go here, or if the force is a little less, the ball might just fall here, right? Or maybe let's just say that this object is here right now, and at the next frame the object is not here but here, it moves. Now the path is clear for our ball, and the ball goes straight up, but now it collides with this object. Now it has again two options: it can either just fall down here, or it can go wherever it has to, depending on the force applied. So in such a situation where we know the initial position, but we have no idea where the final position is going to be, we are supposed to calculate the position of our object repeatedly, right? Repetitively, whatever. So how do we do that? So one way of doing it is by calculating the position of the object at every frame, because see, we are dealing with computers. We don't have seconds, we don't have hours, or we don't have minutes, right? uh, we have frames per second. So how do we do that? So what the method that the way we can do it is by using Verlet integration or Euler's theorem. So before we go on to Verlet integration, we'll quickly just run ourselves over Euler's theorem so that you have at least have the idea of what we're dealing with. So what happens? So we have our object here, right? And that's a very stupid color. Okay, so we have an object here at 0 0 0 position. This is the 0 0 position here, right? We throw a ball up in the air and then it eventually comes down towards here. Now what we have is we have gravity happening. Also, in this case, we are not considering gravity or any other force that might exist, like friction or any other force, like any collision or elastic motion or elastic collision that might come into play. So this equation is just for linear motion, where we know the initial and final position in a very independent and a constricted system of bodies. So now here we are considering gravity. We have our object. This green line is the actual path of the object, and now we are supposed to predict this path. How are we going to do that? We are going to use what's known as Euler's theorem, EULER theorem. What do we do in Euler's theorem? And to TLDR of Euler's theorem is that you add all the forces that are acting on our object to its velocity, right? So let's just say that we have just velocity and gravity acting on our object right now. So we add the velocity. When we add the velocity, the object goes from here to here, right? But then we also take gravity into account, and when we do that, our object is essentially here. So if we call this a dash, a and a dash, so we have essentially predicted the path of our object. The purple line is the predicted path of the object that we have here, and we can go again, we can do this again, and now object is here, and we can go again. I'm sorry, we can go again, and now object is here, and we can go on and calculate this. But you will notice that over the period of time, when we continually do this, the path of an object is going to be somewhat inaccurate to a certain degree. The Euler's theorem is fast, but it's inaccurate, so that's the catch. So what are the solutions? How we can fix this inaccuracy? One way to fix this inaccuracy is that the more we calculate or update the position of our object that we have, the more accurate it is going to be. And to reach 100% accuracy, we'll have to do it infinite times. So like at infinite frames, like at every frame possible, we are going to update the position of an object, which is obviously not possible. You cannot do it infinite times, right? So you can never be 100% accurate, uh, but we don't want to be 70% or 80% or, sorry, not 80, 60% accurate either, right? We want to be at least 90 plus or 95 plus accurate. So how are we going to do that? We do that using Verlet integration, Verlet, Verlet integration. So what is the difference between Verlet integration? The method is essentially the same, but the only difference is that Verlet integration, first of all, is specifically centered around computer graphics and uh, dealing with Newtonian motion, integrating Newtonian motion to calculate the position of a certain object in a digital environment on a computer, right? So the and another essential difference between Verlet integration and Euler's theorem is how it treats an object. So we have points in your what do you call it, Verlet integration, and these points also have sticks. Now these sticks define the motion, how constricted the motion of a certain point is going to be. Anyway, we're not going to go, or we're not going to get deep into Verlet integration, honestly, because reason is that I myself don't understand it thoroughly. I'm still learning it myself, and yeah, that's actually the only reason. So, like I said, that we're not going to be dealing with points in this video, with sticks in this video at least. So let's just start with creating points for our Verlet integration, right? So let's create an array of points, right? And let's just terminate here, and let's push the position values of our object into this points array. So remember, I told you guys that we are adding the positional, the velocity, and the gravity, the value of gravity and velocity, adding on to the object's initial position, and using that initial position and adding these two, we are calculating or predicting the future position of our object. So for that, we need to declare the position values of our object, right? So for that, what we are going to do is we are going to declare two variables. First of all, first one is going to be your x variable, which is going to be the position of the object on the x-axis, and we are going to declare the y variable also, which is going to be the position of the object on y-axis. But it's not just this. If you take this graph again, for example, see, right now the initial position is 0 0, but on the next frame we have this new position, which is going to be the initial position for a future point, which is here. Let's just call it b dash. So for b dash, the initial position of our object is going to be a dash here. So we need to declare these two variables as well. We're going to call them old x. It's going to be slightly different for the initial position, so I'm just going to make it 95, and we're also going to have an old y. Oh my god, why are you this? Okay, 95. Right. So now that we have done it, and now have positional value of our point that we have created. What I'm going to do now is I'm going to first of all comment out this line because we don't need it here. Okay, so we're going to create two functions. First one is going to be update points, right? I'm just defining them, these functions now. We haven't I'm declaring them, these functions now. We haven't defined them yet. And next, what I'm going to do is I'm going to create another function which is going to be render points, and this function is essentially going to render whatever we are doing on the screen. So with that out of the way, what we can do is we can actually define our function update points, right? So we have a function update points, and what we're going to do is, first of all, we're going to iterate through our points array that we have created. So let's create a for loop here, and it's going to iterate through it. And we can start off by creating a variable p, which is going to be equivalent to the current value of positional value of a points array, right? So we have p, which now is now storing the value x, y, and old x and old y, right? And now we need to do is we need to add the value of our velocity. So I'm going to declare two new variables, which is going to be okay. Now we have the velocity here is divided in two parts, just like our position value is. We have our x value and we have our y value, right? So why do we have it that way? To understand it, that in two-dimensional plane we are essentially dealing with a Cartesian plane. So we have the x-axis and we have the y-axis. So if you're talking about velocity of the object, let's just say vx, so it defines that the object is, let's just say vx is equals to 5. So the object is moving 5 units per frame on the x-axis and only on the x-axis. And let's just say we have another variable which is vy, velocity on the y-axis, and it is also equivalent to 5. So that would define or mean that the object is moving 5 units per frame on the y-axis and y-axis alone. And we need to add these two velocity values to our x and y positional values in order to calculate the position, the next position, or predict the next position of our object, right? So we can create vx here, and we can set that this is equal to position um, x minus p minus old y. Oh, okay. Yes, I forgot to explain this line. How exactly do we calculate the velocity of an object? So this is where old x and old y also come into play again. If we subtract the value of old x from our new x and y position, you can actually get the value of x and y, the velocity on x-axis and y-axis. So that's what I'm going to do here. I'm going to subtract the value of old x and old y, and I'm going to save them in the vx and vy variables, right? I'm just going to terminate the statement here. So with that out of the way, what now we can now do is, right, so if you go back to a graph here, this one, like I said, for b dash, the initial position of this object is going to be a dash. So now that's exactly what we need to do. We need to set the p dot our old x and old y to px, right? As easy as that. And wait, why am I getting an error here? I wait. Oh, sorry. Yeah. Sorry. And what do we have here? We can do the same for our y positional value. Now, to calculate the next position of our object, we can do is p dot x is we can add the value to, wait, what is wrong? Velocity value. Now we can add the velocity value here, and the same we're going to do on the y-axis. We can set this equivalent to, wait, what is happening? We can set this equivalent to vy, can't we? Yes. So now that we have done it, what can we do? Okay, so we are practically done with our update points function, right? What we're going to do next is we're going to define a render points function. um oh my god, render points function, right? So it's actually pretty straightforward. What I'm going to do is I'm going to copy this line here from that we had here earlier. We don't need it there, actually we need it in the render function, because we are actually going to render everything here and not in the update function. And what I'm going to do now is I'm going to iterate through. Why is my for loop not working? Anyway, for I is equals to 1, 0, I'll start it with 0, and it is going to be less than equals to points dot length of our array, right? And we're going to increment this value. And what are we going to do now in this for loop actually is we are going to again, we're going to begin the path when we're going to draw the object, and then we're going to fill the object. How do we do this? Again, I'm going to create a variable p, which is going to be equivalent to the value that we have at that point in our points array. Now we can actually begin the path, right? And we can also create the arc now that we have actually begun the path. P dot x value, p dot y value, positional value, and then we can give the size to it, like the radius, and we can give it a start angle 0 and going to be the end angle. I don't math. Can I do this? Yes, I can do this. And the final step should be context dot fill um, here, right? So now that we're done, you might, I don't know if you guys noticed or not, I have started it on live server, so let's just quickly check it out. Ah, okay, it's here. Why is it not working? um this shouldn't have happened. We don't have any error either. What is happening? um why is it not working? Wait, let me just console log here. I'm just gonna say loaded back here and select it again in the console. We are not getting the message. Then this would mean we have yes, we have not connected the script in our HTML document. I'm so sorry. uh, uh, so we have source function. Okay, we don't have an HTTP source. uh, oh boy, what is happening? What's the source of it's Verlet.js. Do we have anything happening on our screen now? Nothing's happening on our screen. What is problem? Can I treat the property get context? Okay. Oh, why would that happen? It cannot treat the property uh, get context of null Verlet.js. It's on the fourth line. Uncaught property cannot treat property get context. Oh boy, what's the problem? Do we have any other message? We don't. Okay, let's try and fix this maybe. I don't know. Okay. Um. So wait, could it be because we have? I don't think actually because of this. We still have that stupid error. But I'm gonna pause the video and I'm gonna like come back real quick and see why we're getting this error. Wait. I'm gonna pause. Okay. So I am back and it is working now. And you can see that this point starts off somewhere around here and moves across the screen. Right. So if you refresh, you'll see that happen. And again, what exactly was the problem? I was wrapping this canvas inside a div, and I actually gave that div the class canvas instead of giving canvas the ID of canvas, because here in on our third line it was getting that it has no information about this canvas thingy, because here in the first line our variable canvas was not able to actually figure out that where exactly is this element on our HTML page. Anyway, let's get back to our JavaScript file, and maybe actually we can, what you can do is have a look at this again. And wow, this is fast. uh, we have created, and what we can do is we can actually add some bounds to it, right? We can actually um, do something so that this ball doesn't just run off from our screen, and actually we can add some edge detection to our object. So to do that, I'm gonna do here is I'm gonna create a new variable called bounce, and I'm just gonna give it a value of 0.9, right? And um, should I do that? I don't know. Okay, yes, we will create this variable called bounce, and I'm gonna give it this value. Uh, how do we go about adding or actually doing edge detection? Right, so we know that if this object here moves across or like goes beyond the screen, we know that it has either crossed, or the value of x and y is higher for what we had originally for our width and height. So it has crossed our device's width and height value. That's why we can no longer see it. It is beyond our scope. So what we can do is we can actually use that for a good use. So if the position value x of our object is greater than the width of a device, what is going to happen is p dot x is going to be equivalent to width, right? And now we're going to set p dot old x is equivalent to p dot x plus Vx. Okay, I'll explain this to you in just a while, but now again, in the Euler theorem, we knew that we can just add the values that we have, just like gravity, bounce, and so on, to our object. So now we have a bounce, and we actually want to multiply this to our, what do you call it, to our object's x value. And now we need to do if it is actually p dot x is less than 0. Right, it's just a little case handling thing that we're doing here, and if it is less than 0, we are going to set should we do it old x? Yes, okay, p dot x is plus vx, and we are also going to multiply this with the pounds, baby. The next we need to do the same thing. What is wrong with you? Why do we have an error here? Okay, so we have, wait, yeah, so I'm sorry. I'm sorry. Anyway, um, we have another if. We need to do the same thing for our height, right? P dot y is greater than the height of a device. Then what we're going to do is we're going to set the value of p dot y is equivalent to height of an object, and then we need to old y is equivalent to p dot y. Okay. Right. Now we also need to do the case handling for if it is less than 0, p dot y less than 0, right? And p dot y is, oh my god, what? I haven't actually slept in 2 days. Okay, so what are the odds that will work? See, are you gonna work? Okay, it's working. What just happened? Wait, we definitely did something wrong here. This shouldn't have happened. um, why did it just like went on and uh, uh maybe increase the value of our bounds. What's gonna happen? It's gonna so what is happening? I have no clue honestly. Um okay, so we're adding the velocities and we're setting the old values here, right? And now we're also equating it with the width. Yes, if it's greater than the width, right? We're gonna set it, adding the velocity, and we're multiplying the bounds. If it is less than 0, then we're gonna set it to 0. Mm, and we're doing uh, we're doing the same thing with the height as well. I don't think we should be doing the same thing for the height as well. Okay. Wait, I figured out why it is happening because this shouldn't have happened. Ooh. Okay. Mm, if it was less than 0, we are setting it to 0. Okay, anyway, let's try adding, I don't know, uh, gravity. Right, we can start with gravity. I'm gonna set it to 0.9 again because that's the value I am actually accustomed to. I have coded this before. I have written this before. I don't know why it's not working right now. Anyway, so we have bounce, and what else do we need? We need gravity. Let's just quickly get with both the forces that I actually want to show you. I'm going to set the value of gravity to 0.5, and I'm going to set the value of friction. I'm going to write friction as well. 0.99. I just know these values work the best because I have done this before. It was basically just hit and trial. Uh, Before we do anything, let's get done with the gravity. Gravity is actually the easiest. So just like we're adding the velocity here, we need to add gravity to the y-axis as well. Y-axis because on our Cartesian plane, the object will fall this way, right? So this is the y-axis. So that's what we're gonna do. So okay, something's happening. We have gravity now, and we have some decent amount of motion. I don't know why. Okay, I have no idea why it's happening. We'll fix it. Um, let's work ourselves with the friction as well. So now friction is actually going to cause problems to the velocity, right? We need what I'm going to do is I'm just going to multiply it with the velocity value of x and y axis. Um, let's wrap them these in a bracket. And no, not like this. We need to multiply these here. If I am not wrong. Oh my god. Right. What kind of motion are we getting now? Okay, so this is nice. This is actually very nice. If you refresh, it's working now. I don't know why it's not working for the width. And why it would just like go on and stick to the width. I'll look onto it. Maybe we will look. I'll give a final check to it. We're almost done here. Like we have the idea now. We can fiddle with the values of gravity and friction. Friction's actually too high. Maybe a little bit too less. Yes. Um. Yes. Yummy. My sense of humor is ruined at this point. So let's just like go through this again. Oh, I figured it out. WIDTH. Yes. Now it's gonna now it's gonna work flawlessly, boys. Yes. Bounce. Oh, did you look at that? Damn. So see, that's how you can work around with physics and everything. And I'm so sleepy. I haven't slept in, oh my god, 2 days. It seems like 5,000 years. Stay safe, stay sound. And let's just see this ball bounce one last time. You know what? I'm gonna make it bigger. I'm gonna make it like so big. Uh, Bigger than your mom. Why? Hey, why didn't it work? Okay, wait. I was actually editing it in the wrong place. Let's just make it 15. Yes, that's nice. Now it's looking actually way better than it did before. Anyway, yes. Stay safe, stay sound. Thanks for watching. Maybe you can try to do this, and if you come up with something better and a newer approach to doing the same thing, let me know. I'll probably learn a thing or two. Anyway, bye.